Hi everyone, good to see you here. So this would be our new home for the continuation of the course. The previous one is going under renovations around that building. I don't want to have the noise interfering. And I know you had to spend quite some time on the exercise. I know it takes quite some time both to solve it and to grapple with it, but also to get into the state of mind and to develop that kind of faculty of estimations, etc. I think that that's the way to do it. If you want to be able to perform later in life in that way, that's the way to get at it. If you have any suggestions for improvements, feel free to share it with us. In terms of things that I mentioned, also relates to these things, I wanted to show some of my favorite books on the subject. So I mentioned this one, Street Fighting Mathematics, which is really developing that kind of skill, not only in the context of biology, etc., but also in terms of other things. So I'll be passing around some of those favorite books. Anyone who wants to have a look, feel free. Make sure it gets back to me at the end.
Are they borrowable from the library?
At least some of them, yes. Actually, this one, for example, is available freely online. So the PDF is available online. So here you can just feel it in your hands, but it's all easy to download in the press of a button. Those who are interested to do these kind of things in the context of the environment, so there's actually two books. One is called Consider a Spherical Cow, which is sort of very often people, when they try to think about something, they say, okay, let's just consider something just a sphere instead of, a bacteria, or instead of something else, or instead of a cow. So that's one, and the continuation was so successful, so there's Consider a Cylindrical Cow, which of course is not as simple, more advanced. So anybody wants to see it, this is all sorts of environmental questions. So I really love these books as well. In the context of energy and renewable energy and helping with that front, there's this amazing book called Sustainable Energy Without the Hot Air by a late professor from England, David McKay. So anyone who's interested in those subjects of energy, really good stuff about doing calculations in that context. People who are looking more into in-depth about cell biology. So this is really the new Bible about the subject. It's called Physical Biology of the Cell. So any aspects that you want on the physics, chemistry, mathematics, thinking about those aspects of the living life of cells, this is great. And it's also by a good friend of mine, Rob Phillips, and his colleagues. Highly recommended. A bit heavier, as you can see. And finally, in many of the exercises you'll see, we're taking the course is really very much related and somewhat based on a book called Cell Biology by the Numbers that Rob Phillips and myself wrote. So again, it's all available freely online, so you can view that also on your phone. We try to make it really easy to access. But if you want to have a look at how it looks when it's printed, you have it all here. Can you repeat that again?
I read your book, and I saw that all these books are listed in the first chapter, in the preface, I think.
Yeah, so I think they're mentioned both in the book and I think maybe even on the website of the course. Okay. As we get started, if anybody has any feedbacks or comments, you can either say now or just come to us later, either on the exercise or on the lecture. And I want to start by going back to the question we ended last time, which is, what is heavier or bigger, mRNA or the protein it codes for? And we also had some options, mRNA, protein, roughly the same or It depends. Okay, you vaguely remember that? Okay, so maybe before we continue, there's this interesting thing, right? Like, I'm doing this writing. I even did it last time, and when I'm doing the writing, it takes time. Do it on the whiteboard, and we're now at 2023. We're all really sophisticated. If I was using a presentation, I could just press, and everything would be there much, much more quickly. You'll be learning more, so sounds much better, right? So, and I could have done it, actually. I have things on slides. Why do I still do it on the whiteboard?
Think while you're writing.
So I need to think, or you need to think?
Think while you're writing.
Okay, so that's one good reason. Any other reasons?
You just love to write on the board.
I like to write on the board? Maybe, yeah.
So people will hear it on Zoom.
People would also be able to connect on the Zoom. Anything else?
Actually, slides would be better for people who really hear Zoom.
Maybe. So really, I'm doing it mostly because of this thinking aspect. I think it's really the process of, the fact that technology now enables us, just throw content at you, like, very easily, does not mean that facilitates learning so much. I think we are kind of like linear animals in such that, like, we understand one thing after another, and the way to write it, I find it for myself, but also for others, is that's more natural in terms of the learning process. And that's why I keep it that way. And if you feel like you're bored and it's too slow, just think about it from more angles. It's time to connect all sorts of parts of things that we're talking about. And I think that's healthy. Okay, so now time to see what you're thinking. Some of you already thought and know about it. So who's voting for the mRNA? Who's voting for the protein? Who's voting for roughly the same? Depends. Okay, so we're starting to lose the it depends answer, but it's fine as well. Okay, so how do we approach it? So I guess, how do we break the problem into parts? What do we need to know? Right, so we want to think about, say, mRNA and protein, and we want to think about, what they're made of and what would be their weight or size. Okay, so what are mRNAs? What are proteins made of? Yeah, so this is, I think, ribonucleic acid is the full name. And protein, amino acids. Okay, and those who are not that familiar with all of those components, not to worry, come to us later. We'll give you like a good chapter in some book, and you'll be going through this without much hurdles. Okay, so we talked about this last time. Anybody remembers what we arrived at in terms of, say, weight?
110.
Again? 110. So I remember only the 10, but 10 to the 2, Dalton. Okay, so it's like 100 hydrogen atoms per amino acid. Okay, now what about the mRNA? How do I think about the weight of the components within mRNA? So again, you might know that by heart, or you've learned it biochemistry at some point, but I'm trying to see how we could derive things from, like, as little information as possible. Like, go to the basic components. So yeah, so maybe, yeah, so looking at the name helps. So we have this thing, which is ribose, which is what? Ribose is, yeah, so this is a sugar.
5 carbons.
Yeah, with 5 carbons. Okay, that's already a lot to know. We could talk about it in a minute. What else do we have here?
Nitrogenous bases.
So we have like a base,
Purines.
which we could talk about in a minute. Anything else in this?
Phosphate.
Yeah, so we need to connect them somehow. So there's also some phosphates here. Okay, so these are the 3 components that build this building block. Let's try to get at the weight of what's happening here. So we have the sugar, which is roughly something like that, some ring. but it doesn't have to be a ring. We said 5 carbon, so what's the weight of each carbon? So that's 12 Dalton. So altogether, I'm multiplying this, and probably there's some other things lying around, right? Some oxygen here and there, or hydrogen. So altogether, I would say I have, say, 5 of these 12s and another 5 of the oxygen, and some number of the hydrogens. Altogether would bring me to about 100. Okay, I'm doing it order of magnitude. Okay, what about the base? So, yeah, so there's all these names, purines and pyrimidines, and Watson and Crick solved how it's all being done with the A, P, G, and C. So I don't remember much about it, but there's some nitrogens there, some carbons there, some oxygens there, probably a few of each. And the weight of each one is somewhere between 10 and to 20 Dalton. So altogether, this again would sum up to about 100 Dalton, or 10 to the 2. And finally, I have these phosphates. How many? I think there's like, there's ATP, ADP.
Yeah, but if it's in mRNA, there's 1.
In mRNA, so I don't even remember. So there's only 1?
Yeah.
Okay, and how much is the weight of each one? Yeah, so I think it's somewhere around 30 Dalton per phosphate. And then it sits with some oxygens associated with it, etc. So on the order of about 100 Dalton also for this. So roughly I have a few hundreds of Daltons. So if here I had 100 Daltons, all of this thing together would be few times 100 Dalton. Actually, if I'm not mistaken, it's somewhere between 300 and 400 Daltons. So we have a factor of about 3. Factor of a few. Is that it? What else? Okay, so this was just about looking at the component, but now there's another factor here that's lying in, which in order to make one amino acid, I need a few ribonucleic acids, right? Not just a few, 3. Okay, so I had a factor of few from here and another factor of 3 from here. So altogether, I have like an order of magnitude difference between the weight of this and the weight of that. Okay, so we're definitely in this situation. Now, I'm interested if you have any thoughts about, what could be the implications? Hi.
Very much.
What are the implications of this understanding? That the mRNA is much heavier than the protein. Yep.
Blueprint is larger than what it codes for.
Okay, good. So the blueprint is like you're thinking about the mRNA, because that's what blueprint bigger than the product. Good. Okay. Which is kind of surprising, right? Like it's not how we, because usually, when we're building this this lecture hall, they had a blueprint. They didn't think about having a blueprint bigger than the lecture hall. And this is really something that goes, so it's, and that's true for most of the things that we're building, etc. So this is against our intuition. And that's why it's actually a good exercise, and why most people usually get it wrong the first time if they haven't heard about it before. Because we bring with ourselves the notion from normal life in thinking also about this. Okay, so that's one implication. Any other things that come to mind when you, yeah?
If the blueprint is way bigger than the product, maybe you can have like few processes of production in parallel. Like when you big like production line, so you can have like a few stations.
Okay, so it means, for example, so you're saying that like you can, there's more place to do things on the mRNA than on the protein. Did I get it right? Okay, so this means, for example, like if you need to do some, right, like much of the cool things that happen in cell biology are happening, say, you know, the mRNA is being formed, and then on top of it, things, you know, bind and change and conformational and whatever. Now you have more of like an intuition that there's a lot of space to do things on the mRNA more than there is on the protein, which is far from trivial. Like I'm not sure how many people studying those aspects. Usually they're just names of things, right? Sometimes you also have them as cartoons. But to put them side by side in perspective, now understand that, hey, actually there's much more place to do those interactions on the mRNA than on the protein. Good, so I agree that this is like an insight that will come out of it as well. Anything else?
Evolution, like it was an RNA world and things evolved from RNA. So biology came up with whatever it found first and didn't really think of it being efficient or.
Okay, so the aspect of the evolution, in general, I would say evolutionary lens is very, very relevant in biology often. So definitely interesting to think about it here. So for example, what did we have first?
RNA.
Yeah, so the understanding is that we started with an RNA world, meaning first we had the RNA, and then we moved into the protein, which now gives you, you know, it's kind of like there's all sorts of things you can say about it. One is that, like, you know, you went from big components into smaller components, right? Which is not unlike what, you know, is happening in technological process, right? Like in our processes of things, we're also moving into miniaturization. So it seems like evolution thought also about that before, starting with the big components and then moving into trying to do similar things with small. So this thing of, like, you know, when you think about, for example, what is like the most, you know, well-known machine that tries to, you know, run things in order to do this process of the central dogma, etc. The ribosome, right?
Yeah.
And here at Weizmann, you know, we're part of, you know, uncovering the structure of the ribosome, etc. And there is this thing about, you know, it started in the RNA world. It was only RNA. Still today, there's a lot of RNA there, but some protein. And, you know, it's been moving in that direction. So it's really, in a way, replacing components of, like, the big things with components much smaller, might be related to what you were saying, efficiency and evolution, etc. Okay, so it can open the mind to all sorts of angles like that. You know, now I can just, you know, I can start hand waving all sorts of arguments. I'm not saying, you know, I can't prove them. We need to then, you know, to create some hypothesis. But now when we have these sizes in mind, you could start having all sorts of hypotheses, which I think is often what's useful in having, you know, doing this sort of analysis. So it could be some sort of like a help in hypothesis generation.
Suppose it also takes longer to put together the mRNA and longer to degrade it relative to the protein.
Okay, so now we could start talking about timescales. Maybe for production, energy invested in this. So, for example, you know, let's say if I'm a neuron or I'm a cell or whatever, and I need to transport things, right? They could be transported often as mRNA, or they could be transported as protein. They could be transported mRNA and then being made into protein. Originally, I might have ideas, you know, is it better to do it this way? Is it better to do it that way? But now I might have different perspective because now I also know what's involved. Like one carries something that's, you know, much heavier, an order of magnitude heavier than the other one. So it has implications for that.
Actually, I learned that neurons, they transport the heavier molecules faster than the smaller molecules, which is kind of counterintuitive.
Okay, so we might get to it in a different lecture about traits.
Yeah.
But just here, I just want to focus on the fact that this is another implication now that you know those aspects of those, key players. Any other thoughts? Anything that I missed that we wanted to highlight?
Regulation.
Regulation. What about regulation?
That many of the regulation in the cell happens in the mRNA level, and you can use its size, and it has many things that affect. I mean, mRNA have like extra capping and stuff to defend it, and they have many places that can react with other stuff, and the regulation happens mostly on this, and this is why it needs more components, maybe, or the more components it has.
So I'm adding it here, if you like. I think that relates to what you were saying. And I think now it surprises me less that all the time people are finding like new regulations and things on mRNA, which originally I said, why are they, what's happening here? Why there's so much, research and stuff happening there? But now in this context, say, hey, it's no surprise because you have so much more real estate to play with. If it's 10 times bigger, there's definitely much more things you can do on top of it in terms of the physics and chemistry of playing around with it. Okay, so I think, as they say, הנושא חפור, but okay, חפור. Okay, so I think we got a perspective on how these concrete things could improve our thinking. Let's take a different angle on sizes and numbers. And let's ask about ourselves. And the question is, and I'll need you to give your honest estimation, is how many atoms are in your body? Okay, simple question. I'm guessing you don't know, it's not written in your ID. But still, I want to start by just, throwing out like a very rough guess. Okay. I would ask, most of you to bet on the number. So, who's going to start? 10 to the 27. Anyone else?
I would add a number, 10 to the 23.
10 to the 23. Okay, I need more. 10 to the 40.
Googleplex.
How much is Googleplex?
It's
10 to the 100.
10 to
Yeah.
the 10 to the 100. I think.
Yeah.
Okay. Anyone else? Feel free. It's like nobody's. Yeah. You don't 10 to the 16 or 17. Let's make it 16. 10 to the 75. It would be best if I have close to the number of people around. So, throw some. To the 90? 19?
No, 90.
We'll take them both. Anyone else? 10 to the 30.
To the 33.
33. Okay. What do we do next? So, there's two approaches from here. One is try to really, do the hard work of estimating, or not so hard work. We'll try to do it street fighting type. So it would be, so we could arrive at something without taking too much time. But there's also another way that, has been developed by humanity for like 2,000 years, which is democracy, right? Like, we got the views of different people, and now we just, we take, the democratic result of that. But there's two ways in order to make the call based on the democratic view. So we have all of those numbers, and we need to bring them together. Right? What's the usual way to do that? Right, you take the average. Good. Let's take the average. So how much is the average? I need to do, let's call it mu, 10 to the 27 plus 10 to the 23 plus 10 to the 40 plus 10 to the 100 plus 10 to the 16 and divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I love it. By 10.
Geometric average.
So just a second. So how much do I get?
10 to
10 to the 100.
Yeah, so it's 10 to the 100. Okay, so we're doing the democratic average, but it's very heavily dominated, by one factor. Okay, there's another option that was mentioned here, which is,
The geometric mean.
so yeah, so we could take what's known as the geometric mean. So that's I think this is called the arithmetic mean. There's also something called the geometric mean, which is what? You take the average of the exponents. Okay, so that's like it's 10 to the 27 plus 23 plus 40 plus 100 divided by 10. It's this. There's more formal definition of geometric mean, like if I have x1, x2, x3, I want to take the geometric mean, I just multiply them, x1 times x2 times, and then I take the 1 divided by n power of that. Okay, well, like to make it simple, if I have, let's say, the value of 1 and 100, what's the average of that? The normal average? So it's 101, 100 plus 1 divided by 2, it's like 50. Geometric mean is 1 times 100 square root, which would be square root of 1 times 100. This would be 10. Okay, well, if it was 1 in the million, square root of a million, it would be 1,000. Okay, which is like making the regular average of the. Okay, so did anyone calculate that by any chance? Okay, you want to do it together? 50, 190, 206, 281, 390. Already did it some other way? 390, 420, I think 453 divided by 3. So I get 442.
35.
If I'm not mistaken, I got 42. 45. Anyway, we could check. Okay, it's quite different it's a different of like 60 orders of magnitude. So, we should pay attention. 60 orders of magnitude is not something to be taken lightly. Okay, but now this is like if I had to guess, I would tend to use when I need to take the democratic average of things to go with the geometric mean because that protects me from like crazy values. Okay, and I think you'll find this is a very very useful trick in many ways. There's another way of taking the median. I won't get into that. That's another statistical valid way to go at things. Now let's put it aside for a second and try to do it more properly, okay? Well, let's leave the democracy for a minute. We might get to it later. And the question is, how do I estimate the number of atoms in my body?
the atom, and we know how much it weighs, and we also know how much we weigh.
Fantastic. So we could say let's focus on the most abundant component, which is water. And then on water, we could start doing something. Okay, what do we do with the water? How do I connect it to the number of water atoms I have in the body?
1 mole will be 18 grams.
Okay, so this is a good direction. Like remember from last time we said, very like here we want to move again from the macroscopic world, the world of the body, to the world of atoms, the microscopic world. Usually what is called wormhole or whatever, like things that moves you from this universe to that universe. The Avogadro number is like the door to take you from this world to that world. And there you just have to think, how do I connect these things, right? So you could connect it by knowing, okay, this thing, you could know this weighs, in terms of mass of water, it's 18 Dalton. How do I know that? Because this is 16, and this is twice 1. Okay, so I got 18 Dalton. Okay, we'll get to it in a minute. And now I need to look from the other direction at the weight of a person. And now this wouldn't be in Daltons. How much is the weight of a person? So I know 70 kilos, right? Okay, so now I want to do the following. This is the weight of the overall water. I'm interested in the weight. I want to go with the number of atoms. So I want to know the mass of an atom. How much is the mass of, the average mass of an atom in terms of Daltons? Yeah, so we could divide it by 3. I would say it's about 10 Daltons. And the mass of a person, let's turn it into 100 kilograms. Okay, how do we connect between the Daltons and the kilograms?
Convert kilograms to Dalton.
Okay, so in order to do that, let's first convert it to grams, okay? Because the grams and Daltons what usually speaks with each other. So 10 to the 2 kilograms, that's 10 to the 5 grams. Okay? And now what's the connection between gram and Dalton? That's the Avogadro number. So the number of moles in a human is the mass of a human divided by the mass of the atom. This is about 10 to the 5 grams divided by 10 Dalton, which is actually, in terms of units, 10 Daltons is, I think, 10 grams per mole. That's what I was missing. Okay, look what I did now. Okay, these calculations, they could be really confusing. And very often what really helps me, if I can, is if I can follow the units. This is actually a complicated example to do it, so not the perfect example. So those of you who get it, that's great. And those of you not, don't worry, we'll come back to it maybe at some point, it will make more sense. But Dalton is like the number of grams per mole. Okay? And then when I write it this way, then I say, grams and grams, that's fantastic. 10 to the 5, 10 to the 1, meaning 10 to the 4. And I say I'm left with number of moles. Okay, so I got the number of moles. So each one of us is 10,000 moles. Okay. What that means about the number of atoms in a human? So that's 10 to the 4 moles times the number of atoms in a mole. You might remember it. How much is that?
About 10 and
10 to the 523.
Yeah, so this 6 times 10 to the 23, which we agreed that at least for our course, it's good enough to think about as 10 to the 24. And therefore, we're getting about, that each one of us is about 10 to the 28 atoms. Okay, so we were still 14 orders of magnitude away, but much better than being, 80 orders of magnitude away or 70 orders of magnitude away.
Somehow I expected us to be more than 10 to the power of 4 moles. I don't know, by intuition.
So we're expecting us to be more than 1,000 moles,
Yeah.
10,000 moles.
Hmm?
It's
More than-
10,000.
more than 10,000 moles.
10 to the power of 4.
Okay, I'm happy that you're saying it out loud, because really that's what we're trying to do, like to improve our intuition on things. And only when we reflect on the fact that we thought something and now it's not what's happening, then we understand we actually learned something new. Yep.
I lost what the 10 to the 24 represents.
Yeah. What did the 10 to the 24 come from? Yeah. So also I didn't write units here, so it's a bit confusing. So 10 to the 24 is the number of, it's in units of atoms per mole. Okay? And you can say, where did that come from? So it came from this guy Avogadro, which got the name for n, and this is 6 times, I don't remember what, times 10 to the 23. And this is like the definition of a mole, and they got it through, now we could, it's basically how many atoms of hydrogen there are per gram of hydrogen. Okay, or 1/12, how many atoms of carbon there is in 12 grams of carbon. So it's really by definition this thing of how to move from things that you measure like grams in the lab into how many things there'll be when you look under the microscope if you're able to count the atoms. Thanks for asking. Okay, so now you can do, I think in one of the courses we had somebody now then calculating how many moles are in a mole, the animal, and stuff like that. And any more, so I think we did this, and that, and here, and now, and we'll be moving ahead. Any more comments or thoughts about this? Okay, so
We are not considering the atoms which we give out by breathing or by excretion and stuff, but won't make that much of a difference.
yeah, so he's saying this we were just, so what did we take here about the components of a person?
Water.
Not much, right? Like we just said water, and even in the water, we very quickly just convert into saying, okay, the weight of an atom is roughly 10 daltons. In that respect, really for that kind of question, I don't care, if you're eating, energy bars or steaks or drinking milk, all of those things, not so important. And actually, if instead of water, we would have talked about, sugar or lipids or something else, also would make very little difference. Because the components there, all this, hydrogen is like 1 dalton, all the rest is, over 10 daltons, carbon, nitrogen, phosphate, oxygen, On the average, it's roughly there. Which is nice in a way, like you really, for some things, you need to know very little in order to be able to give the relevant answer. Okay, so I want to leave you with one thing, like one question to take with you for the recess. And that's also in the spirit of like checking our intuition. So I know you're coming from diverse backgrounds, but yeah.
Sorry for being late. How can you neglect the other 30%? Because it might be built of much more atoms per gram, so it might be relevant in terms of scale, right?
Okay, great point. So you're saying, we analyze just water. It relates also to the question before. I think it's interesting. Okay, you're saying, maybe the other third is just a third, and this is 2/3, but maybe that is, much smaller, much bigger, something like that, and that offsets everything.
Because you look at the atoms and not weight, so there might be like enormous amount of atoms, but that are weighing less, and then it gives you a much larger number for this 30%.
Okay, so the question is, maybe it's, something that weighs much less, and therefore the number is much expanded. That's the point, right?
Yeah.
Okay, I would say it's kind of like the same flavor, like driven, as the previous question of okay, we were so simplified here in just talking about water, but what do we eat? What do we excrete? How does that affect, etc.? Okay, so what's the answer? Anybody wants to suggest?
It doesn't differ that much because we mostly carbons and nitrogen.
So let's think what could be there. Like, what did we use? We used water, which I just deleted, and we said the point that got into the calculation is this 10 Dalton. That came from the component, some of it being hydrogen, some of it being oxygen. Okay, now the question is, what surprises could we have in terms of those other components in the 1/3? And actually, the table of the elements does not give us much to play with. Like, it can't be anything below 1, because, at least hydrogen, that's the lightest. We're probably not made of uranium or something like that, that's in like 100 Dalton. But, even if we are, I chose the 10, which is kind of like the geometric mean between the hydrogen and the uranium. And, maybe I'm wrong by what? Let's say you have something crazy there that is 3 times more or 3 times less. We made out of boron or made out of strontium, I don't know what. It would give me a factor of 3 on this 1/3, that maybe would give a factor of 2 somehow. But we were talking about 10 to the 20 something versus 20 to the 4, it wouldn't change. There's no way it would change the order of magnitude. And that's the point. It's really, it's like a simple question, but it's like a very strong point here. For some of the things you'll be doing, all of those, gut feelings that we have that, it depends, and we have to know what are you excreting and what exactly atoms are there, and why do you simplifying so much? For some problems in life, it's important, and for some problems in life, it's just not like you can do the estimate and it would be very robust to all the rest. And see how, it's interesting because the two of you asked a very similar question, and this is after, you came to this course knowing in a way that this is what I'm going to feed you. And we had the previous lecture, and we talked about it, and then we did an exercise in that spirit. It's just like our gut reaction keeps on going back to this thing of trying in a way to complicate things, because that's what we learned for years and years and years, how to complicate things. And that's fine. We came to the Weizmann Institute to learn, how to solve some of those complications. But for many things, the path of trying to do something quick, simple, etc., would give you a lot about the answer. Again, the alternative is usually not knowing, like you don't know anything about the number of atoms in the person. Okay? Good. So to get us to the recess, let me ask you the following. So how many of you ever grew cells like bacteria, put them like for, there's like overnight or something they want to do? Okay, so it seems like more than half. And some of you haven't, so I'll just tell you, if you're in a biology lab or some of the chemistry lab, that's like kind of like the most standard thing you do because you want to do some manipulations on DNA, on this, on that. So you're just taking, like a test tube with, some media. Usually you have their, okay, we'll talk about in a second. You're throwing in some bacteria that you just want to have a lot of them for tomorrow for an experiment, and you let it sit overnight until they grow what's called into saturation. Meaning that, just gets full of bacteria, they ate everything they had there, and now they're waiting for you to come in the morning and start going. Okay? And my question is to, improve our intuition is what takes, just a second. Okay, we'll do it in two parts. What takes a larger fraction of the volume? I want to know about something about the density. Bacteria in a saturated overnight culture or the students in our class. Okay, like if I was taking you in the class within the volume of the class, or the bacteria inside the test tube within the volume of the liquid in the test tube. What does your intuition say? So, bacteria, students, roughly the same. Oh, depends. What? Oh, I started with a single bacteria. No, I take all of the bacteria that are sitting within the test tube after they grew to saturation, and I look at the volume that they take out of all the bacteria in the test tube. Okay, it's good. I see people are starting to talk among each other. It seems like you're curious about this. So let's first your intuition. So who's voting for the bacteria? Seems like the most. Who's voting for the students? A few. Same. Also few. And it depends. Nobody. Okay, we eliminated that. Okay, big progress. Okay, I think I will leave you for we'll take a 15 minutes recess, and you can try and think how you would break down this problem if you try to estimate it. If you already have the solution by the end of the recess, even better. Okay, so we're back. Before we go back to our bacteria and students in terms of density, a few updates came from things mentioned. First of all, so we are in the second lecture, and you have the second exercise already online. You have until the next lecture in order to hand it in, but luckily for you, there's Christmas next week, so we won't have lecture on the 25th, I guess it is, and the next lecture would be on the 1st of January 2024. It's happening, it's coming. So you have 2 weeks to hand the next exercise. Try to not to do it on Sylvester night or something like that. I think it's better to start earlier. Still, if you need more time or anything like that, do let us know, especially those that I know listening to this, the recording, etc. I would also mention, both to you but also to your friends or to those on the recording, those who can come to class, it's better that you do come to class. I hope you see why, because much of the learning is through the interaction. I think the recordings are high quality, but it's not the same. And if those who are just listening to it and can't come, or if you can't come, you need to both watch it and then send us some feedback on something you learned from it and something you suggest to improve in it. Okay, so in 2 weeks we'll be meeting here, January 1st. Then I had 2 comments that came from during the break apropos the number of atoms, which I thought are worth mentioning. One is that somebody was telling me they gut reaction was, or like in order to give a really fast answer, they said, you know, if I met somebody in the street, they asked me how many atoms you're made of, you would tell them Avogadro number without doing all of this. And I think that's a good answer. That's like if you want, like in, you know, like in the Taylor expansion, like this is like the zero order. Right? Like it's a good zero order when you need to know and do this connection to the microscope. You just say Avogadro number. And then when you have a bit more time, you can say, it's not Avogadro number, it's 10,000 Avogadro numbers. But that's not a big deal, it's just 10,000 fold. So, you know,
Someone comes to
it's,
me
it's,
and
it's the next best answer. Okay? And then there was another person who said they actually did the derivation based on the size of an atom, based on sizes. So let's just do that for a second. There's advantages and disadvantages. But if I want to think about the size of an atom, anybody carries a length scale for that? Angstrom. So what is an angstrom?
10 plus minus 10.
Yeah, so angstrom is a good size for a hydrogen atom, or in general, like for an atom, and that's 10 to the minus 10 meters. Okay, so how do I connect this into a person? All right, so let's talk about for a second. So the size, the length of an atom is roughly 1 angstrom, which is 10 to the minus 10 meters.
it's the diameter, not the size, right?
Yeah, diameter, size, we could talk about. You know, orders of magnitude, I think will be fine. Okay, how do I connect it to a person? So by volume, that's good. So the volume of the atom would be 10 to the minus 10 cubed, right? I can think about it like as a cube, right? It's not a cube, it's a sphere, it's a cylinder, it's a quantum magic. It's like 10 to the minus 30 meters cubed. Thanks. Okay, what about the person? What's the volume of a person? Let's say the person weighs 100 kilograms. Okay, what does that mean about the volume? So the density is water, like 1. Okay, so if instead of 100 kilograms, we weighted 1,000 kilograms, what would be the volume? Yeah, so 1 meter cubed. 1,000 liters, 1 meter cubed. But we're not weighing 1,000 kilograms, we're weighing 100 kilograms. So that's like 0.1 meter cubed, each one of us. Okay? So 10 to the minus 1 meter cubed. So if I just take these two things, I divide them, the V of the person divided by the V of the atom, I have 10 to the minus 1 divided by 10 to the minus 30, which I'm getting 10 to the 29, which is atoms per person, which is not that far off from the 10 to the 28 that we did in a different way. Okay, so that's another way to approach it, which is quite elegant. Good. So that's a few, and it might even connect to what we said before, because you remember we had this question, and now I want to move towards the answer to this. But the question is, what is like in this, divide and conquer approach? How would you go about breaking it down? So the most basic step is to say, okay, let's talk about bacteria in the culture, and then talk about humans in the classroom, right? It's two different things. We'll start with the easy one or with the hard one. So which one is the easy or which one is the tough one?
The one we can see is the easy.
Yeah, so I think usually the things that you can see here in the class, we could do it pretty easily. And then the things of bacteria, we need to infer all sorts of things. It's tougher. And then I actually had a student in the lab, and we always had fights, because every time I say we get a review for a paper, I like to do the easy things, to get rid of it and clean it. And he always said, it's useless. If we don't solve the hard problems, we won't make any progress. He always wanted to start with the tough things. And we were quarreled all the time, whether to do it this way or that way. So let's do it his way this time. We start from the tough one. Okay, so in order to do that, let's start with a question. What percent of volume is taken by saturated culture of bacteria. Okay, let's give a few options. It's like few tens of percent, which you remember we could write as this way. Or few percent, or point few percent, or much less. Okay, we're talking about like we had this, we put the bacteria, we let it grow, and now we come back, we have this muck of, some, yellowish bacteria, and the question is, what is the fraction taken up here? Who's voting for a few tens of percent? 10 people. Who's voting for few percent? 15 people. Point few percent? 5 people. Who's voting for much less? Nobody. That's interesting. Can you raise again who ever grew bacteria? Okay, the vast majority. Okay, so the vast majority grew bacteria, but the answer to this is not completely clear. And most of you are wrong. So that's good. Okay, so how do we approach this? Any ideas? Yeah.
I can speak from my experience. So an overnight culture is about OD5, and one OD is like 10 to the 8. So you can know approximately how many bacteria are in 1 ml, and then divide the volume of the bacteria. That's how you do it.
Good. Okay, so this is one direction. Hopefully we'll do it soon. Any other directions?
We counted how much cycles the bacteria amplifies before it's saturated, and then did the same thing for the saturated.
Okay, so first option was about, you carry on this number about like how many cells are in OD, and then we could do the calculation for the number of cells. In other ways, related to this, you first know something about like doubling time, and from the doubling time, you can know number of cells, and then you do similar trick. Good. Other, strategies?
Just from experience, when you do the centrifuge and look at the volume of the bacteria out of the superatom, so it's about 1%.
Okay, so then you're saying, I have my intuition, I just, I centrifuge them, we look 1%. Okay, you're very good intuition. 1%.
No,
Right.
I grow 500 milliliters and I get 5 milliliters of bacteria after the centrifuge.
I agree with you. That's good. Any other suggestions? Okay, so first of all, I'll say, we had 3 suggestions. If I need to cluster them, they're like quite different in terms of their sensitivity to, like, if we do the calculations, there's all sorts of things that could go wrong at some calculations. Some of them are more robust. Which one do you think are the more robust one, and which one could go wrong out of those 3 strategies?
I think the last one where you estimate by eye can go wrong because some amount of liquid or fluid will still be there even if you mix and blend it. Just that they are super concentrated.
Okay, so you're saying, this sounds, less reliable, right? Okay, good. Let's start with your approach. Okay? I never did it that way, so let's do it. How would you do it?
So we estimated that we have in the starter a few 10 by the power of 6 bacteria.
So you're starting with, some millions of bacteria.
Yes, and it for 10 hours, which is somehow calculated that it has 2 to the power of 30 cycles, which is
All right, just 1 second. Okay, so he says, we start, with these things. Those who didn't do it, no worries. You might actually get a better answer than the others. So that's good. You're throwing in some bacteria that you scrapped from something. So let's say a few millions. There's a question how much we're dependent on what is the exact number, but we'll see. And then the next thing you're saying, it's 10, you left the lab. We won't tell your PI. You left at like 5 p.m. No, probably if you want 10 hours, you must have left like 8 p.m. and you came at 6 in the morning. Okay.
saturation. It sounds
Because then they stayed in saturation. Okay, so you left at 4 p.m., 10 hours, and midnight they got into, or like 2 p.m., and then from there they finished growing. Okay, 10 hours, good. And then you're saying doubling,
Doubling is, each cycle is 20 minutes.
let's say 20 minutes doubling time. Okay, and you infer from that.
So it's 30 times doubling.
Okay, so from this and that, you see what's happening here? 10 hours, and you're doubling every 20 minutes, so you have 3 doublings every hour. So altogether you have
2 to the power of 30.
2 to the power of 30 fold increase. Okay, what do we do next?
We converted it to the tens to the power of. I'm not sure that we did it right or not, but we got 10 to the power of 5.
Okay, so how do we know if 2 to the 30 is 10 to the 5? Yes or no? Okay, so there's different. Okay, so one trick is to say 2 to the third, which is 2 times 2 times 2, it's 8. 8 is like 10. I actually have a better one. Okay, just for the fun of it. How much is 2 to the 10? So it's 2, 4, 8. When I can't fall asleep, that's what I do. 2, 4, 8, 16, 32, 64, 128, 256, 512, 10,024. Okay, which is nice because that's like really close to 10 to the 3. Right? So you can impress your friends every time you want when you need to do these things. Every time you have 2 to the something which is large, you can take every 10 and make it into 3, and that's 10 to the 3. Very useful. Okay, so this is like 10 to the 3 times 3. 10 to the 9. Okay? Everybody with me, more or less? Feel free to ask. That's really the engine behind the good lecture. Okay, so
I feel that this approach can be a little faulty because bacteria don't grow linearly. They have a lag phase. And then the doubling time, 20 minutes is not exact. It depends upon how much oxygen they get. So it could be somewhere between 30 minutes.
yeah,
So
I think you're right, but it's too late because I asked you before, and you said this would be the better method, and her would be more sensitive. And now I'm proving that you were wrong, so it's too late to say it now. But I agree. Okay, so you see where it's heading. Okay, so I have 10 to the 9. What's next?
So we get few to the power few times 10 to the power of 15 bacteria, which is times micrometer to the power of third the volume of the.
So few times 10 to the 15 bacteria. Okay, so what do you do from here?
We infer the volume, which is 1 micrometer.
Okay, so far so good. You got the few 10 to the 15. And now we want to go from this to the volume that it takes. Okay? So how do you do that?
Multiply it by 1 micrometer to the power of third because
Okay, so you need to take, this is the number of bacteria, and you want to multiply it by the volume of the bacteria, which is, yeah, so it's 1 micrometer times 1 micrometer times 1 micrometer, so it's 10 to the minus 6 meters cubed, which is 10 to the minus 18 meter cubed, right? Good? Okay, I'm sorry that I'm all over the place, but it's actually, I'm enjoying myself. Okay, what's next?
next we
Okay, so what's the volume of the starter?
Few milliliters.
Okay, so we're starting with few milliliters. That's the volume of starter. So what is few milliliters?
It's few 10 to the power of -3 liters.
Okay, it's few milliliters. Milli is a 1,000th of a liter. Few 10 to the -3 liters, which is
10 to the power of -6 meter cube.
fantastic. Few times 10 to -6 because I'm going from liters into meters cubed, and there's 10 to the 3 liters cubed per meter cube. Okay, by the way, those of you, it's pretty quick for some. That's fine. We have the recording. Take your time. Concentrate on it. There's things to be learned. Okay, few times 10 to the -6 meter cube. That's the volume of the starter. Good. What did we get for the volume of the bacteria?
Few 10 to the power.
So we had few times 10 to the 15, right? Times 10 to the -18. So we're getting few times 10 to the -3 meter cube. Right? So, what did we get for the density? What?
Few bromide. Few bromide. For me.
So, what is the result? I heard different things. So, I see some people looking like this. 0.
Much more volume of bacteria than volume of the starter.
Oh, it's the opposite.
Yeah, so it's a bit confusing, right? We got not 0.1% what it seems. That would have been if we dividing this by this. But we're dividing this by this. Right? The density is the volume taken by the bacteria divided by volume taken by. Okay, so I really laid the trap for you and you fell through.
We did a calculation and it went out fantastic.
That's fine. You helped me much more this way. Okay? So really what we got is a volume of bacteria much, much bigger than the volume of the starter. Okay, so paradox. What?
It doesn't calculate the saturation
Why?
because it only, the calculation is based on doubling time, but it doesn't consistent to double overnight because it reaches the saturation.
Yeah. So okay. So the Achilles heel of this calculation is sitting. These things could be sensitive. It sounds like a really good strategy, but then there's you're assuming like exponential growth. In exponential growth, things could go like crazily wrong. There's this example of if bacteria were growing exponentially, if I don't remember, like 3 days, they would be the size of the moon. Right? Or they would reach the moon, or both. So this thing of assuming 10 hours, 20 minutes doubling, which sounds very sensible, is very, very dependent on whether you use 10 hours or 8 hours, 20 minutes or 30 minutes. It's highly sensitive to this. And these are numbers you don't know very well. You think that she didn't know well 1%. You know much, much less. This is much more sensitive to this. Because there, it's definitely true that she could tell between 1% and let's say 10%. Or 1% and, point something. But here, you have this difference between 20 minutes and 24 minutes that would turn out to a much, much bigger effect in the exponential after 10 hours of that, okay? So there's this thing that is sometimes, not intuitive, but what is robust and what is sensitive. And you have to be aware of. Okay, so this method is highly sensitive, even though it sounds like very intuitive, and also it sounds like, very scientific, like very good. I put also, but actually it's much worse than the more intuitive thing. Okay, it's like it got us 1,000-fold more than full saturation. Like it really got us like 1,000,000-fold or something wrong. Okay. I could say more about it, but actually that's already like couldn't be much better. Let me just see about the time. We're out of time. Wow, what do we do? Okay, we could do the other method that was suggested based on like this 10 to the 8, etc. It would be much better, but still could give you something wrong. I would say there's two methods which are much more robust and help you. One is this thing. Look at, it's about 1%. By the way, I think, it depends. It could be somewhat less because they have, usually you grow it in these flasks that look like this, right? And you fill it to here, and then you see they're here, right? And this looks like 1%.
I'm
But then,
not talking about the starter, I'm talking about the culture. It's more accurate. If you're taking culture after the starter, taking the culture of 500 milliliters,
okay, yeah.
and you...
That's fine. Okay, I'm just saying, you can centrifuge. You see something in the bottom. It's hard to say whether it's 1%, 0.1%, etc. Also because of the conical shape, etc. But you'll get roughly the right thing, and then you can actually do it in some other. Do you know like how much food do you give them when you're growing it? Usually when you make media. Anybody making media? At Weizmann, we're just getting it from microbiology, so it's too easy. But usually when you look at the recipe, it's like 0.2% or something like that. Like 2 grams per liter or something like that. What? 8 grams, maybe it depends on the recipe. Let's say you do it with 8 grams or 2 grams, etc. per liter. What does that mean? So it's 2 grams per liter. That's 0.2%. Okay, or 8 grams per liter, that's 0.8%. Okay? So that's what we're putting them in terms of food. What happens with that food? Some of it is thrown away, and some of it turns into new bacteria. Right? So how much are you going to get out of it?
Less than the food you give them.
Less than the food you give them. So there's like no way it would be this. And actually no way it's going to be this either. It's going to be something like this. Okay, and also bacteria are not stupid. They're not just throwing it all away. So this is the answer. And we could derive it in different ways, but I'm just showing you there's some robust ways to do it when you think about the essence, and there's some less robust, etc. Okay, now we could do the thing about the class. Let's do it super quick, or try. So what's the fraction of the volume that you're taking here? What do we need to know? The volume of U and the volume of the class. What's the volume of the class? So what's the length here? 10 meters. What's the width? What's the height?
4 meters. 10.
Few meters. Okay, so altogether we have few hundred meter cube. Right? Okay, how many of you are here? Few tens. What's the volume of each one of you?
0.1 meter cube.
Yeah, 0.1 meter cubed per student, right? So if we multiply that, how much are we getting? Few times 10 divided by 0.1, so few meter cubed. Okay, and now we need the ratio, so it's few divided by few hundred, so that's about 1%. Okay, so that means that the fraction of the density occupied by the students is somewhat higher than the bacteria in saturated. I wouldn't make a big deal out of it. Like it's somewhere between this and that. Okay, it's like 1 order of magnitude. It depends on did you put 8 grams per liter, 2 grams per liter. I'm not making a big deal out of it. But our intuition that the bacteria want much more, that's wrong. Okay, it's somewhere between same or you're more dense. Okay, actually, if you think about it, so first of all, it means like, you might now understand a bit better about like, those bacteria. They're not so close to each other. And I think that's important to know. They're not like touching each other. They're like flowing in liquid, and sometimes they're meeting friends there. Okay, and also you can think about yourself in class. You're kind of like a bacteria in a, the class is like a bacteria in saturated culture, except it's not a regular class because like it's in 3-dimensional. So it's like a yoga class. Everybody's floating. It's like meditation. Everybody floating in there, and that's roughly like how you can think about being bacteria in the cell culture. So the last thing I want to share with you is something that would prepare us for the next meeting. So we've been talking about sizes mostly, and sizes are intimately related to concentrations and numbers of things, as we touched on some of those. So let's take a concrete example from the microscopic world, and that is I'm looking inside a cell. I'll often be thinking about bacteria just because they're like the simple organism to think with, but then you can also scale it to other cells. And I'm thinking about the bacterial cell, and I'm asking about like one of the basic components that you have there, which is called hydronium ions. Okay, so there's this H plus or H3O plus, which is this thing related to acidity and many reactions and things like that. And I would like to know in the bacteria that I'll be in some bacteria, how many H plus atoms are in a bacterial cell. When I'm thinking about bacteria, there's actually a lot of variety in the bacterial world. So let's think about an E. coli cell, not unlike the things you've already been playing with. And we'll start with our intuition. So is it about 10 to the 2, 10 to the 4, 10 to the 6, 10 to the 8, or 10 to the 10? Is the question clear, just to see that we're on the same page? So we're talking about one of the components that takes part in many of the chemical reactions, biochemical reactions, on the membrane, coming in, going out, lots of H pluses, being discussed in the textbooks. And I'm saying if I'm taking a bacterium and asking, and I go and count them inside the cell, how many do I have? Okay, let's take a quick vote. Who's voting for 10 to the 2? 1. 10 to the 4? Few. 10 to the 6? 10. 10 to the 8? Another 10. 10 to the 10? Another few. Okay. Few or less of you are correct. But we'll have time to go deeply into it and test our intuition and why is it so wrong next time. So I remind you, next time is in 2 weeks from now. We'll be meeting again here. You have the new exercise available. Start going through it. If it's too tough, let us know. Ask a friend. You can work on it a bit together. That's also fine. And just hand it by the right time. And all the best.